Hello, I'm Professor Rad, and this is Precalc video 112, even and odd functions. In this video, we'll be discussing the properties of a function being even or odd. Now, a function doesn't necessarily have to be even or odd. It could be neither one of these two properties. So we're going to talk about what these properties look like algebraically and also graphically. So let's dig on in. So if you have an even function, the formal definition is that f of negative x is the same as f of x. What this means is if you have a point xy on your function, then you also have the point negative xy. So if your function passes through the point 5, 7, it'll also pass through the point negative 5, 7. If it goes through the point negative pi 3, it'll also go through the point positive pi 3. So the negative and positive values of x share the same y value. This is going to result in symmetry over the y-axis. So if you were to reflect this function over a y-axis, then it would look the same. So those are what it means to be an even function. To be an odd function, we have some similar stuff going on, but a little different because they're different. So for an odd function, f of negative x is the same as negative f of x. What this means is if you have the point xy on your function, you will also have the point negative x, negative y. So if your function is an odd function and it passes through the point 1, 2, it'll also pass through the point negative 1, negative 2. So this time, instead of the positive and negative values of x having the same y value, the positive and negative values of x are going to have opposite signed y values. This is going to result in symmetry through the origin. So we'll do a few examples, both algebraically and graphically. The symmetry is what we're going to use to determine graphically if a function is even or odd or neither. And but we're going to start out with the algebraic because the algebraic work for a problem like this is akin to a proof. Think determining evenness and oddness as starting out with f of negative x and simplifying that expression. You want to work within one equation, not within like separate disjointed pieces. So I'm going to show you what that looks like, kind of what your work or your approach to the problem might look like, and then what your final write-up needs to look like. So let's put an example on the board and walk through it. All right, so I've got my little reference sheet over here on the side, just a reminder of what even and odd functions are. And for this example, we're going to do a few different functions, and we're just going to determine whether they are even, odd, or neither. So for our first function, we have x to the 4th minus 6x squared plus 11. So this is going to be an algebraic problem. To start out with an algebraic problem, I'll stand over here so I'm not totally off screen. So notice that both of the even and the odd involve f of negative x. So here we have f of negative x, here we have f of negative x, and then we want to simplify that expression to see if we get f of x or negative f of x. So to establish whether a function is even or odd algebraically, you want to find f of negative x and simplify it, and then compare it back to the original function. So I'm going to start out by finding f of negative x. So that means wherever I see x, I'm going to replace that x with a negative x. So this is negative x to the 4th minus 6 times negative x squared plus 11. Now, because we are having a negative sign with this x, we want to make sure that we include those parentheses. If you have a negative value raised to an odd power, it's going to remain negative. But if you have a negative value and you raise it to an even power, it's going to become positive. So what this means is if I have negative x to the 4th power, that's going to be the same as just x to the 4th. Over here, I have a negative x being squared, so that's not going to change the sign here. That's going to remain a minus 6x squared. And then I have my plus 11. All right, so now I have this quartic. There's nothing else I can do with it. So I'm done with the simplifying step. Now I have to do the comparison step. Is this result the same as my original function? And if so, then it's even. or is it the same as the oppositely signed function? In that case, it'll be odd. So here, when I compare x to the fourth minus 6x squared plus 11, x to the fourth minus 6x squared plus 11, I got the same function. So this is the same as f of x. So this is the sort of work that you're going to need to show when establishing algebraically whether a function is even or odd or neither. You're going to want to start out with f of negative x and then work in a single column, kind of like you're simplifying the expression as opposed to solving an equation. So you don't want to start out with, a statement of equality and then simplify and moving stuff around, because you're supposing what you want to conclude before you're able to conclude it. In this case, what this is saying is that f of negative x is equal to f of x. So we would say, therefore, these three dots are therefore, f of negative x is equal to f of x. Now this meant that we have an even function. So we can conclude, therefore, f of x is even. All right, let's do another example and see what we get. Another one algebraically. All right, so for our second example, we have g of t is equal to 2 over 3t. So to figure out whether or not this function is even or odd or neither, we're once again going to start out by finding g of negative t. So g of negative t. That means wherever we see t in the expression of the function, we're going to replace it with negative t. So this is 2 over 3 times negative t. Now here we have a positive times a negative, so the result's going to be negative. So we have 2 over negative 3t. All right, so at this point, there's a little stuff that we could do. If we really wanted to, we could pull that negative out front. Actually, why don't we do that? Why don't we pull the negative out front of this expression? So this is the same as negative 2 over 3t. And we could throw that negative up top, but now we're just like messing with it to mess with it. So that's about as simple as this expression is going to get. We've done all the work we can here. So now we want to compare this final expression with the original. So we have negative 2 over 3t, and we started out with 2 over 3t. So we got something different from g. So we know that kind of in the back of our head, we know that this is not even because g of negative t was not the same as our original function g of t. So we have a negative 2 over 3t. We started out with 2 over 3t. They're not the same. So I know that this is not an even function. So now I'm going to see, is it odd? And if it's not odd, then it's going to be neither. So to be an odd function, f of negative x needs to be the same as negative f of x. So what you might do on scrap paper, if you have difficulty seeing what the two sides might end up looking like, you might say, okay, well, what does negative g of t look like? What does that look like? So negative g of t is going to be the same as if I took this expression and then negated it. So that's going to be negative, and then just this friend here, 2 over 3t. So this is what negative g of t looks like. So negative g of t is negative 2 over 3t. So let's see if that's what we got. So it is, we got negative 2 over 3t. So to finish up what I'm writing, I'm going to write, this is negative g of t. So we have g of negative t is the same as negative g of t. So therefore, g is odd since g of negative t is equal to negative g of t. So I'm kind of spacing out my work in this manner because this is one of those problems in math where some of the work that you are going to do does not end up in your final write-up of the problem. So in this case, we had this work over here. This is like what we're thinking about, or this is what's done on scrap paper. And this may not make it into the final version of the problem. Whereas something like this is our final write-up. Think of it like when you go to write a research paper and you're taking notes. These are your notes for the research paper, and this is your final paper. So not everything you take notes on ends up in your research paper. Maybe you choose to use a source or not use a source last minute. So I didn't really need to know this piece because ultimately I needed this g of negative t and negative g of t. So this bit of research I ended up using. So I'm going to do another example where some of this process might look a little bit messier. All right, for our third and final algebraic example, we have h of x is equal to x minus the square root of x squared plus 2. So if you want to try this one on your own, first you can. We're just going to find h of negative x and simplify. So if you want to pause and try this one out, feel free. Otherwise, work along with me. So h of negative x means wherever I see x in the expression, I'm going to replace it with a negative x. So instead of x, I'm going to have negative x. Instead of x squared, I'm going to have negative x squared, and then plus 2. All right, so now we simplify. So negative x, I don't really need to put the parentheses here. So I can just rewrite that as negative x. And then negative x being squared means negative x times negative x. So that's going to become a positive x squared plus 2. Okay, so that's our simplified form of the function. If I go ahead and compare it to the original, it's awfully close to the original, right? So this x squared plus 2 is showing up in both of these pieces. But in the original, we had x, and now we have negative x. So these are not the same function. So over on my scrap paper in the back of my head, I'm thinking this one is not even because h of negative x is not h of x. Now for this next part, it can sometimes be challenging to see whether or not our final result is the same as negative h of x. So we can go ahead and work that out on the side here to see if what we got is going to be the same as the negated form of this function. So negative h of x, that means I'm going to negate this whole thing. So we have x minus the square root of x squared plus 2. So now if I want to negate that, that's going to be, distribute this negative sign, we get negative x minus a negative is plus the square root of x squared plus 2. So if I negate h of x, I end up with this expression here. So if I compare this expression to what we ended up getting, it's again really similar. We have this x squared plus 2 under a radical, and now we even have this negative x. But the difference is this time with negative h of x, we have a plus, and with negative here, well, yeah, we have a negative here. So we have two different operations. So they are not the same function. So this means that h is not odd, since h of negative x is not negative h of x. So again, this is all kind of going on our scrap paper or in our thought process, but this is not necessarily what shows up on our final result. So for our final result, we want to continue with this simplifying, and we want to get to a point where it's abundantly clear we have neither the original nor the negated form of the function. So to do that, I want to get it in the form where I have negative something, because then I can see it's really not the original and it's not the negated form. So what I'm going to do here is I'm going to factor out this negative sign. to get x plus the square root of x squared plus 2. And once I have this, it's now clear I have negative an expression, which is not the same as this expression here. So I can conclude that this is not h of x, and it's not equal to negative h of x. So I've got my conclusion. It's not the original function. It's not the negated form of the original function. Therefore, h of x is neither even nor odd. And that would be the end of our problem here. So notice that this work over here is helpful to us in determining whether it's even or odd, but in writing up our kind of like proof, in writing up our justification for our response, some of that may not make it into the final form. Okay, this is just here to kind of help us identify or make that comparison more easily if we're not comfortable leaping to this conclusion right away. So now that we've done a couple of examples algebraically, let's do a few graphically. So I'm going to sketch a few graphs and we'll decide graphically whether they're even, odd, or neither. All right, for our graphical example, what we're going to be looking for is symmetry over the y-axis to indicate that it is an even function, or symmetry through the origin to indicate that it's odd. Excuse me. Now, I have a difficult time seeing symmetry sometimes, so I also use the ordered pairs to help guide me in making this decision. That's not so much the case with even. The symmetry over the y-axis is a little easier for me to see, but symmetry through the origin is a little bit tougher, so I like to do the comparison with the ordered pairs. So to do this problem, we're going to check all of the common functions that we talked about in an earlier video for this unit. So, excuse me, I got a frog in my throat apparently. So what I'm going to do is just quickly sketch the image of each of these common functions. So this is an instance where you want to have those common functions at your ready access so that you can visualize them pretty quickly. So the identity function is y equals x, so it's going to look like that. The squaring function is y equals x squared, so it's going to look like this. The cubing function does a little shimmy like that. The reciprocal function has a couple of asymptotes on each axis. And then we have this downward slope here. The square root function is going to start at 0 and then it goes off like a sideways parabola above. The cubed root kind of looks similar to this, but it's got a slightly different sort of shimmy happening. The constant function, these were families of functions, are going to look like horizontal lines. The absolute value function looks like a V. Exponential functions have this sort of shape. They have a horizontal asymptote. And then we're looking like this, increase pretty rapidly. Logarithmic functions have a vertical asymptote, and they look kind of like this. And then, oh, the greatest integer function had all these little line segments, like so. All right, so now that we have our common functions sketched out, let's identify whether they are even, odd, or neither. So the first thing I'm going to do is do a quick scan and see if there are any that are symmetric over the y-axis. Those are the easiest ones for me personally. Those are going to be our even functions. So with the identity function, if I fold this in half, it doesn't match up. This piece would end up over here, so this one's not even. The squaring function is though, because if I take this piece of the function and reflect it over, I get the same thing. So that means that the squaring function is even. And we're just going to do that for each of these. So this one is not the same. This one is not the same over there. There's nothing over here. This one's not the same. This one is, right? So we have this horizontal piece and this horizontal piece. So this one's even. So is the absolute value because we have this piece here. And if I were to reflect it, I would get this piece here. Exponential functions are not even. The logarithmic function is not even. And the greatest integer function is not even either. So that's our first pass through these functions. We've identified which of these are even. So it looks like 3 of our original functions ended up being even. Now let's see which of these functions are odd. So to determine if a function is odd, we want to see if there's symmetry through the origin. So this is where I use the ordered pairs of the points to kind of help me out. So for instance, here, I would have the point 1, 1. If I'm going to be an odd function, I also have to go through the point -1, -1. And I can see that that symmetry is going to maintain through the origin. If I have the point 5, 5 over here, then I'm going to get -5, -5. So the identity function is odd. For the cubing function, we're going to get a similar thing. The cubing function goes through 1, 1. Let's pick a messier point. It goes through 2, 8. It's also going to go through -2, -8. So again, we have this nice symmetry happening. So the cubing function is odd. And then we're just going to go through the ones that we didn't mark even and see if they're odd. So the reciprocal function is going to be odd. We have this symmetry here, like 5, 1/5. So if we go to -5, -1/5, that works out. The square root function has no negative side here, so it can't be odd. The cubed root function is odd. It's very similar to the cubing. The exponential is not. If I were to reflect this through the origin, I'm not getting anything down here, so this one's not odd. Same thing with our logarithmic functions. If I were to reflect this through the origin, I'm not getting anything over here, so this one is not odd. Ooh, and the greatest integer function is kind of sneaky. So I'm going to pick this point here. It goes through the point 1, 1. And let's see, so it also goes through the point -1, -1. So you might be tempted to think that the greatest integer function is also going to be odd. However, something about the graph of this function seems a little bit off to me with regards to that symmetry. Like this line segment here is on the x-axis, but I don't have anything matching it on the x-axis over here. So this is because if we pick something that's not an integer, we'll actually see that we don't get the pairs to line up properly. For example, the greatest integer function goes to the point 1.5, 1. So if I go over to 1.5, and I have a y value of 1. But if I go over to -1.5, I end up down here at -2. So I have an xy value, but I don't get -x, -y. I get -x something different. So it's not enough just to check 1 or 2 points. You really have to be able to justify it for all. So using these ordered pairs can help you kind of establish that symmetry if you have difficulty visualizing it. But you want to make sure that you can appropriately justify that symmetry for all points. So it looks like in the end, the square root is neither even nor odd. The exponential functions are neither even nor odd. Similarly, logarithmics are neither. And our greatest integer function here is neither even nor odd as well. although it looks like it's odd, but it's not, it's neither one. All right, so it looks like we have 3 of our common functions are even. 1, 2, 3, 4 of them are odd, and 4 of them were neither even nor odd. So if you wanted to add these properties to your notes where you were writing about those common functions, you could do that. That's going to conclude this video on even and odd functions. In the next video, we're going to be doing a similar kind of like proofy thing when we talk about whether or not a function is one-to-one. So I hope this video helped you with even and odd, both algebraically and graphically, and I look forward to seeing you in the next video. Bye for now.